Okie dokie, folksies. So we just got finished talking about primary, secondary, and tertiary wavelengths, right? So the question is, there's a lot of information here. There's a lot of information between the lamp and the burner head and adjusting and aligning everything. And is it acetylene gas? Is it nitrous gas? What wavelength should I use? What is the linearity now that I know that? How far can my standards go before they're no good anymore? There's a lot of questions. And because of that, there's a lot of recipes. And there's a lot of recipes, you put everything in what we call a cookbook. Well, guess what? We also have what we call the Atomic Absorption Cookbook. And right up here at the very top, you actually will see that. So all of the machines will come with a cookbook. And this is just basically a reference sheet. And that reference sheet is going to tell you everything you need to know about the element that you're trying to measure. It tells you the details because we know that an analyst is never going to remember every single detail. So, for instance, here is a cookbook page for the metal aluminum, right? And they typically will put them in alphabetical order, and it just so happens to be the first metal that's listed in the cookbook. So, up here at the top, you're going to see something called analytical lines. And this is 309.3, 396.2. This is in reference to primary, secondary, tertiary wavelengths. That's what that is referring to. Okay? Down here at the box below, you'll see the parameters. And it looks like the flame here is preferred nitrous. So it's going to take nitrous, mix it with a little bit of acetylene and air, and it's going to require a hotter flame in order to do the aluminum analysis. So this is how I know which kind of gas tank I should be using. Most of the modern instrumentation will automatically choose the proper gases when you choose the element now. This is something that's embedded into the software, and it automatically refers to the gas that should be preferred when measuring the element. The HCl current. HCl stands for hollow cathode lamp, right? This is the bulb, and the bulb we talked about needs a certain voltage, and that depends on the bulb itself. So typically, aluminum, based in the cookbook, should be running at a 5 milliamp current. Basically, I need to make sure I go into the machine, I make sure that the milliamps or the voltage that's given to that lamp is no more than 5 milliamp, and that's what I should be running when I analyze aluminum with the aluminum bulb. The PMT voltage is something that you don't have to worry about anymore. This is an issue that has been taken care of. Typically, the PMT voltage and the detector is ran at the same place, at the same time, at the same strength. So no longer do you have to worry about the detector. The slit width. The slit width we talked about. This thing is very important. What's the width of the keyhole that the light goes through? And in this case, 0.2 is the width of the light path. So 0.2 nanometer. Characteristic concentration. Well, this is 1 milligram per liter. And the working range is 0.3 to 100 milligrams per liter. This is part per million. Characteristic concentration, 1 part per million. Working range, 0.3 to 100 part per million. On the cookbook page, you will also see an area that will tell you how to prep an aluminum standard if you had to prep one yourself from scratch. Typically, these metals are ordered, and these metals are prepped from a liquid solution. 1000 ppm is the typical concentration. And then finally down here at the bottom, you see some interferences. It says aluminum is prone to ionization in the nitrous oxide flame. So we need to add potassium or lanthanum to alleviate the interference. If you have silicon, calcium, and phosphate, the absorption is depressed. But if you have iron, titanium, nickel, and manganese, the absorption is increased. So this tells me there's going to be some fluctuation with the absorbances depending on my metal concentration. And this is where I find all of that information. Over here to the side, you will basically see linearity. So if we look at very low concentrations, it looks pretty straight up to a certain point, right? But after a certain point, it begins to curve and it will begin to deviate from a linear line. Here is a different cookbook from a different AA instrument. Notice it looks different, but the same type of information is present. So this is the same for aluminum as we saw before. It just gives me a little bit more information here. And this is actually the instrument that we have. This cookbook is very similar to the one that we have in our laboratory, which is why I'm showing it to you. So here in the previous one, it only listed like the top two, and this one will list every single choice typically that you can use easily on the AA instrument itself. And they will typically list them in order of priority. So this one is primary, this one is secondary, this one's tertiary, this one's quaternary, and so on. So the wavelength is listed here. That would be the primary wavelength. If I was measuring aluminum, I would want to go into 309.3. The slit width, well, it's at 0.7. I want to make sure that it's at 0.7 every single time I run an aluminum sample. Notice for primary, secondary, tertiary, and quaternary, they're all the same. Not in every metal's case, but in this one it is. We have this column called relative noise. We don't really want a noise value that's very high. Noise is basically trash, some type of signal that the instrument's giving me that shouldn't be there. So the higher the noise is, I probably don't want to be choosing that wavelength in order to run because I want a very clean baseline. I don't want a lot of crap going on in the background that I have to worry about. The characteristic concentration check. This is something that is on this sheet, but it's not on the other cookbook. And in our cookbook, different ones are different, so make sure you take a look at your unit that's provided. But the characteristic concentration check is a way for you to double check that the machine settings are correct. Because in our version, if I make that particular concentration, I should get a 0.2 absorbance every single time. That is how our cookbook is written. Different cookbooks are written a different way. But for us, if I make that concentration, it should read a 0.2. If it gets close to a 0.2, I've done my job the proper way. So if this was my cookbook, that 50 part per million I would make, and I would run that first. And if I get something to a 0.2 absorbance, then that means all of my settings are correct. My lamp is aligned, I've chosen the right wavelength, I've chosen the right voltage for the lamp, my burner head is aligned the right way, I've got the right amount of gas going into it, my temperature to the flame is proper, my nebulizer tube is sucking up sample at the proper rate, everything checks out. That is the purpose of a concentration check. 50 milligram per liter for aluminum. The linear range over here to the side will tell me how linear can the instrument go using this wavelength. And it looks like this can go up to 100 part per million. Then it's pretty much linear. As before, down here at the bottom, you're going to see a way to prep your own standard if you had to. The interferences, just like before, they're stated here as well, and the ways to fix them. And This one talks about this thing called a doublet, which is something that you do not have to worry about. We're not going to get into that. That's more for method developers and more advanced kind of topics in atomic absorption, and we don't need to go into that topic now. This cookbook page also talks about flame emission, not just atomic absorption. So if I did not want to use a bulb at all, and I want to measure aluminum that way, I can measure aluminum using nitrous oxide acetylene. I just don't plug a bulb in. I make sure that it's 0.2 slit, and then I make sure that I dial in at 396.2. At 396.2, remember, that's an emission line. That's what's given off. We'll look up here. 396.2, it's also an absorption line. That makes sense, right? If it absorbs, it also has to emit that particular place. So it gives me the best setting if I want to run this on flame emission and not atomic absorption. So here is the cookbook page for copper. And copper is just like aluminum. The setup is the same at least. So it gives me a primary wavelength. It gives me the slit width that goes with that wavelength. And it gives me the calibration check. So for this instrument, the calibration check is a 4 part per million. And that 4 part per million should give me a certain absorbance value. Again, ours is different. Our machine uses our settings to do a concentration check. And I'll go ahead and tell you that for copper, our concentration check is 1.5, not a 4. And that 1.5 should give me a 0.2 absorbance. Everything is in reference to a 0.2 absorbance on our machine. So this machine's different. This is a Perkin-Elmer cookbook, and that's why the numbers are different. But the primary wavelengths are the same, the slit widths are the same. That's not going to change depending on the atom. What will change is how well the instrument is made, and that will be your calibration check. That's where that fluctuation is going to happen. Notice that the linear range here is at 5 part per million. Anything after a 5, it deviates from linearity, and you probably don't want to use it. 327.4, really close to the primary. That's the secondary. Same slit width. The concentration check here is an 8. So the linearity is still a 5. Now, what does that mean? Well, that means that my linearity is the same as primary. However, this thing is slightly more insensitive to the sample analysis, which means I probably could go a little bit more outside of the linearity range if I wanted, but it's not recommended. So secondary wavelength probably would not be used here for that purpose. However, tertiary wavelength, you see a big change. Tertiary wavelength is 216.5. The slit width that goes with that is a 0.2. Not only that, but the calibration check is much higher. It's at a 20. Run my 20 part per million. Make sure it meets the instrument parameter settings. If so, I'm good to go. I can run samples. And this linearity range goes to a 20. All right, so to a 20 means that this is a more concentrated sample, higher levels. I can go a little higher on the calibration curve. The problem is that it's going to not do me justice at the lower end of the calibration curve. I trust it more in the mid-range than I do at a 0.5 or a 1 or a 2 part per million. If you go to quaternary, quaternary goes to 222. That calibration check is way higher to get the same type of signal. And because of that, the calibration curve can actually take a 50 part per million sample. That's where it's going to be linear. Down below, you'll see the flame emission, just like before. The stock standard, if you have to make your own, it gives you the recipe. And then the light sources. Anything special about the light sources or anything special about interferences will be listed down below. Each of the pages of the cookbook are separated and divided up by element in alphabetical order. And then either in the beginning or at the end of the cookbook, you will see a summary chart. We actually have one of these summary charts up on our wall beside of the AA instrument in the laboratory. This summary chart is also included in every single light bulb box that we have near the instrument. So you can always have access to the summary chart when needed. But basically, the summary chart will list all of the metals that you can analyze with the AA instrument. It gives you the primary wavelength. It gives you the slit width that goes with that. It gives you the gases that's going to be required for that metal. And it gives you the concentration check that's required for that metal as well. It's a very quick reference to the cookbook pages. Now, if you need to know information about the secondary, tertiary, quaternary wavelengths, then this summary table, of course, is not going to do you any good. There are versions of cookbook summary tables out there that do list more than the primary wavelength. Ours does. So you're going to actually see more choices under each element. But because we prefer to run everything primary, primary is what's listed on this chart because that's what people will do the most of. So there's the summary chart of everything that's in the cookbook, and it's a very quick and handy reference for you. Notice down here at the bottom, it says that the metal concentration, milligram per liter, in aqueous solution, which will give a reading of a 0.2 absorbance unit. That's typically what all of these instruments are referring to. How low can I go, or what concentration is needed here in this table to give me a 0.2 absorbance? Again, double check your instrument parameters. Double check your cookbook. They will always define what this characteristic concentration check should be. So, double check it, but for this cookbook, you see down here at the bottom, it's a 0.2 absorbance. For our cookbook, it's in reference to a 0.2 absorbance, and for many of them, that's how they're kind of standardly made now. So you are now a chef of the atomic absorption spectroscopy world, and you have now been presented the cookbook, which is all the recipes that you can do in a laboratory when you use the atomic absorption instrument. This cookbook is found in our laboratory. You can see it at any point in time. We have a photocopy that's made, and we stick it in our drawer near the instrument. The cookbook summary table is also up on our wall near the atomic absorption spectrometer, so that way you have a quick and handy reference for when you need it, and you don't have to go digging or try to find it. And this is a staple that you will always use in a laboratory because it basically will tell you what you can and cannot do. All right, so we have somewhat finished up the lecture on the pieces and parts and the theory of the instrument itself. And there's a couple of different variations of atomic absorption that's out there. And I want to take a few minutes and maybe a few videos and go over some of these choices that you might see in a laboratory. So in the upcoming videos, we're still talking about atomic absorption and atomic emission. But there's some different things that we can do, different attachments that maybe we can utilize to maybe do a better job. But with those attachments come more money. So the question is, do you really want to go through that or not? But we'll at least touch base. We won't go into a lot of the detail and a lot of the theory on it, but we'll briefly mention them, tell you that they're out there, tell you what they're used for, and that way you'll be more well versed in the field of AA and AE.